So now I'm going to erase all of this and make some room so we can quickly talk about how this applies to diprotic acids. Now, diprotic acids actually have two potential buffers associated with them, which will be important for our titration. So we have two buffers. And that's because we have two different conjugate pairs to worry about. The H2A, which is in an equilibrium with the intermediate and the proton. And so in principle, you may have a buffer where you have a pH equal to pK, we'll put in the subscript momentarily, but for now pK plus log of HA minus, which with respect to this equilibrium is the conjugate base, even though it's also an intermediate and can behave as an acid, but in this context it's behaving like a conjugate base. And then the acid itself, H2A. Now, as for that pK value, well, we have two to choose from for the diprotic, right? pK1 and pK2. So which one do we pick? This is the easy part to mess up. And the answer is we pick the first one. Why? Because the equilibrium between H2A and HA minus involves the first proton being lost. And so K1 is the relevant equilibrium constant. And then we can do something similar for the equilibrium between HA minus when it behaves like an acid, according to the second dissociation, K2, and then produces A2 minus as its conjugate base, and we have a proton. And we set up the Henderson-Hasselbalch equation. It's very much the same, except instead of pK1, we are now dealing with pK2. And the ratio that gets plugged in here is different, because now HA minus is actually functioning like an acid. So it goes on bottom, and up top the conjugate base is A2 minus. Now let's be clear, if one of these is in solution, they all must be in solution, because all of these reactions happen, including the conjugate base reactions with water that I haven't bothered to write. But typically, one of them is going to be very negligible compared to the other two. And while we can try to use the Henderson-Hasselbalch equation to figure out which one's dominant at a given pH, it's actually easier to represent things as a number line. So now we're going to draw a pH number line, where left represents low pH, right represents high pH. And I'm going to mark off a couple of very important values on this pH number line. One is when the pH is equal to the pK1 of whatever diprotic acid we're dealing with, and as you can probably guess, the other point I'm marking off represents when the pH equals the second pK value. And using similar logic to what we've seen in the past, we can assert that when pH equals pK1, that must mean that these two are equal, and similarly when pH equals pK2, these two concentrations are equal. So let's write under pK1 that at that particular pH, the concentration of H2A must equal the concentration of HA minus. And over at pK2, when the pH equals that, HA minus must equal the concentration of A2 minus. And so it should stand to reason that if the pH was, say, any higher than that pK value, if it was any more basic than that, that equality would be broken and the A2 minus would be dominant. So we'll call this region of the number line the A2 minus dominant region. All the way on the left, when it's more acidic than pK1, that's where H2A is dominant. And of course in between, what else could there be besides HA minus? So let's draw some points along this number line and see how we interpret everything. Let's put an asterisk here. Let's put a triangle right in the middle of the HA minus region. And somewhat to the left, let's put a circle. And then to the right of pK2, let's put a plus. And don't worry if you don't make things look exactly like mine. It's all qualitative. So now I want to ask at each of these points, what is the order of dominance between our three species? So let's start with that asterisk. Well, the number line clearly shows that at this pH, H2A is dominant. So what's second dominant? Is it the intermediate or the fully deprotonated base form? And hopefully you're thinking it's the intermediate, which it is. At these relatively acidic pH values, the basic form is going to be very negligible in comparison to the other two species. And so let's write, at this pH, the acidic form concentration, H2A, is greater than the intermediate form concentration, which in turn is greater than the fully deprotonated base form's concentration. Now how about we jump all the way to the reverse situation, where we're clearly in the A2- dominant region? Well, this dominates over HA-, which in turn dominates over H2A. So let's write that. At the plus sign pH value, our order of dominance is concentration of A2- is larger than the concentration of HA-, which in turn is larger than the concentration of H2A. Now I'm going to clear some space for the other 2 points. And let's do those, starting with the triangle, which again was at the midpoint, which mathematically means that the pH must be equal to the average of pK1 and pK2, or 1/2 times pK1 plus pK2. Where have we seen that formula before? Well, that's the formula for calculating the pH of a solution that begins as pure intermediate. In that particular scenario, the concentrations of H2A and A2- are equal. So what we'll write is that HA- concentration is definitely dominant. But as far as the acid form and the base form, well, these concentrations are equal, only at that midpoint. And so it should stand to reason that if the pH were to drop lower than that midpoint, then this equality would be broken and the acidic form would start to dominate over the base form as we get closer to its dominant region. And of course, vice versa. If we went higher in pH, this would start to overtake the H2A. But anywhere in this region, HA- is still dominant. So for the circle, we will write circle is going to be HA- is greater than H2A, which in turn is greater than A2-. And the logic is that pH is closer to pK1 than pK2. pH is closer to pK1 than pK2. And after this, it makes sense to do a clicker, which we will cover in Zoom.